let's start to get started. First question is, are there any questions about anything from last time about backtracking or anything like that? Okay. How many people have gotten all 4 of the backtracking problems done? Nobody. How many people have gotten 3 of the backtracking problems done? Nobody. How many people have got 2 of the backtracking problems done? Nobody. How many's got 1 of the backtracking problems done? See, 1. That's good. How many people got 0 of them done? Okay. Is that because people aren't trying it at this time of year, or because they found that there was difficulties?
I didn't have time to do this.
Didn't have time. Okay. Tried the 15 puzzle one, and what happened?
I actually haven't submitted it yet. It's just been, on the test case that I'm running, it's just been taking a long time, so.
Okay, so let's talk about these. What I think I'm going to do is, how many people here, who here wants me to review, maybe as one more practice before we do it, maybe let's just take a quick look at how you would solve, I would solve the 8 queens problem. Just to provide that background. I didn't really do that last time. So let's just do a quick look here. Because I think that certain things, like the question of how fast, how you speed these things up, maybe become easier when we look at a representative problem with pruning. The other examples I gave, except for my bin backing thing, which I wildly did on the board, were all for relatively simple problems. 8 queens is more representative in that it's a problem. You have an 8x8 chessboard. You want to put 8 queens down. Okay? Let's just go through this one quickly. You have an 8x8 chessboard. That's a 2x2. 4x4. Well, let's leave it at 4x4 by now. Your goal is to put queens. Queens in chess have the property that they can attack along diagonals or rows. Here is a solution of the 4 queens problem, where you can put down 4 queens that don't attack each other. The question really is to find, in this problem, all possible ways to place 8 queens on an 8x8 chessboard, or in general, n queens on an n-by-n chessboard. Okay? Any questions about that? Using our backtracking representation from before, what would be a good representation for our board, our solution? Okay, let's just think about, remember we had a generic backtracking program that worked on building up a vector, solution vector. What would be a logical solution vector for the 8 queens problem? Okay?
Position.
What?
Position.
Positions of what? Okay, so how many spots in our vector?
8.
N.
8.
N or n squared. Notice that there's 2 possibilities for thinking about this. One possibility is we build a solution up by having a vector of n squared spots, where each spot we either have true or false, depending upon whether or not there's a queen there. Does everybody agree that's one possibility? You're suggesting something different, I believe, right?
Yeah, the
What are you
queen's
suggesting?
position. The queen's position.
You're saying one interesting thing is that if we have n queens and n positions in an n-by-n board, because the queens can attack along a row, along every horizontal, you can't have more than 1 queen per row. And if you want n queens to go on the board, you have to put 1 in each row, right? So based on that observation, one way to write it is to have a vector of size n, where each spot has a number from 1 to n, telling you what is the column that that queen is going to be in. Does everybody see that? Which is a better representation? Both of them give you ways to encode solutions. Which ones of them are better? Okay? Does anyone want to make a proposal? Okay, why do you like yours better?
Because if you only mark the the map, then it's hard for backtracking.
Well, backtracking, it's not so much that it's hard for backtracking, because backtracking we did on the true, false, all subsets thing. What I'd say more precisely is it's hard for pruning, right? Most of your placement steps will be putting in falses. There's only going to be 8 trues, ultimately, right? So a lot of your time is spent basically putting in blank things. Okay, this is a much more concise representation. There's 2 to the 64th possible representations here. How many representations are there here? There's 8 to the 8th. What is 8 to the 8th? How does that compare to 2 to the 64? Okay? In principle, a lot better, right? That's going to be what? That's 2 to the 3 to the 8. Okay? Which means I believe that's 2 to the 11th. Am I right? Right? Okay, or 2 to the 24th. 2 to the 24th. That's still less than 2 to the 64th, right? Okay? So this is a more concise representation, and that makes it better. Okay? Are we right? Okay, good. So what should be, if we're now going to represent it by a number from 1 to 8, what is the, do we have a solution? Remember, there's 3 things that we need to fill. One is construct the candidates for the next spot. Another is, do we have a solution? And finally, process solution, right? If we wanted to just count the number of solutions, process solution is basically every time we have a solution, add 1 to it, right? What are the candidates for the next spot? Suppose I filled in the first 3 spots in my vector. What are the possible candidates for the 4th spot? This is going to be, in the 4th row, what are the positions which are not yet attacked by one of the 3 queens? Does everybody see that? In this case, this queen attacks this one. This one attacks this one. This one attacks that one, that one. There's only 1 candidate here, right? How do we tell if we have a solution? Complete. Since we're only putting down legal queens, if we put in enough of them, then we're done. Does everybody see that? And so if you look at it that way, my solution is actually looks like this. Construct candidates. Basically, just goes through, again, exactly how you implement this is a little, is up to you. In my way of doing it, basically I went through and decided what, this is my bookkeeping. I'm not going to go into the detail, but basically I accounted for all existing queens. Okay, which squares get threatened by columns, which ones get threatened by diagonal moves, and then picked out which candidates that remain. Okay, if I is still a legal, so I guess right, I tried for every square. What I did was, I then take a look at all existing queens and said, does any of the existing queens threaten that square? If it doesn't, add that square to my list of candidates. Okay, that's the basic logic there. Any questions? There's different ways you can do that bookkeeping, but that's that. Process solution, just add 1 to the count. Is it a solution? Is everything filled up? That's the 8 queens problem. Any questions about how I did that? Okay, using the Skiena backtracking method. Those of you who are doing backtracking, are you using your own backtracking method or are you using the Skiena backtracking method? Is there anybody who's using the Skiena method? My code, for example. My code is on the web, so you're free to look. If you look at programming challenges, you can get it. Okay? You're free to start from the Skiena backtrack procedure. Or you can use your own. Is there anybody who's starting from mine? Okay? Those of you who are starting from your own, is that because you think it's better or because you didn't know it was available? It's fair to say either. My feelings won't be hurt. Okay? Any questions? But if I were doing it, I'd start with the Skiena backtracking method. Any questions? Okay, so let's look at the problems for today. Which problems do we want to discuss first? I am going to propose that we discuss the 15 puzzle first as being the, let's say, less varnished backtracking one. How many people have tried the 15 puzzle? Okay. How many people have tried the Little Bishops one? It's about the same. Okay. But let's do the 15 puzzle because I think that's going to be the more vanilla backtracking one. Somebody who's tried this one, tell me how they did it. Tell me what the problem is and how they did it. Okay? Somebody.
For a 15 puzzle?
Yes, what is the 15 puzzle? Let's try this. Boom.
You have those little sliding palette things that you have to move around.
Right.
And you have to rearrange them in a way that that's the solved version.
Right.
You can get that. So basically, you just swap.
Okay. Okay, so basically what our goal is, again, we can slide a tile, okay, represented by basically we can slide the hole. People talk about moving the hole instead of moving a tile. We can think about the hole as moving up, down, left, right, okay? And it asks you for, given an input configuration, what is the smallest sequence? Okay, what is a short sequence of moves to solve it? Okay. Any questions about it? It doesn't ask for the shortest, but it asks for one that is not that long. Is that right? So how do we represent this in my configuration space? Okay. Let's first look at it my way. I know you're doing it in a similar way. But if we will look at a solution vector, what would be the solution vector that we would want to have to represent a solution? Okay? What is the solution vector in this kind of a model? What is it that the I thing represents?
The number in that cell.
Well, one possibility that you're saying is you want a solution vector to be a number in that cell. So you're going to have 16 puzzle spots, right? That isn't, to me, a solution vector. That is a state of the board. Did people see what the difference is? Because the solution vector ultimately is going to be, when you get the 1, 2, 3, 4, 5, 6, 7, 8, 9, blank, that's the solution, right? I don't need backtracking to find the optimal solution. Look, I just did. Okay? But that didn't help you solve your problem, right? So we've got to distinguish between two different things. There is the board state, and there is the solution state. Does everybody see that? And the solution state is what we're searching for. So what would be a solution vector that would represent what we're doing here? We want to try to use the Skiena generic backtracking. You're free to have done it another way, but let's just think this through for a second. What would be the solution vector here?
The characters leading up, down, left, right.
So one possibility would be a sequence of up, down, left, right. Okay? And that you're filling them in, right? And our goal here is to find a solution where at the end of it, okay, what we've got is is a solved state of board. Does everybody agree with that? So I like this solution vector here. Okay? Fair enough. So if we're going to do this now this way, what is the construct candidates spot? What are the candidates for a particular for this? What are the candidate moves for this spot? Okay. Which one would it be? What would be how would I construct the candidates for the next spot in my solution vector?
You should check whether the empty squares are either.
First question is, where is the the empty square. Does everybody agree with that? The empty square has a position based on the current prefix, right? And so one thing I'm going to have to do is to compute what the empty square is, right? And if the empty square is at a boundary, then I've only got either 2 or 3 moves, okay, as opposed to 4, right? So that's one thing I can do with this thing. What is a solution? When do I know I have a solution? How do I check?
The stage of the block.
I would compute the stage of the board for the entire state so far, right? And if at that point my state of the board is, as you said, 1 through 15 with a blank there, then I'm done. Does everybody agree with that? That's what is a solution would be. And what would, What would process solution be in this particular problem?
Just output the sequence of the move.
One thing would be to output, so if my solution is short enough, then output it. Does everybody agree with that? Right? So that would be basically what process solution is. Is there any way I can now refine this idea to make the search faster? You just started giving a hint at this a little bit, or maybe you didn't. At least one hint came up. Is generating the move purely a function of seeing what square it's at? Or is there ways that we can avoid searching more stuff by changing our construct candidates move? Right? So let's just think about it. If you implement this, this is going to be too slow, is my prediction. That's what you found, right? How do we speed up this basic approach? Okay? We have to do pruning, is the biggest thing you have to do. Part of you may say, well, gee, I'm spending a lot of time recomputing the state of the board. That, depending upon how you use local variables, you might be able to get a little win there. But when I'm trying to speed up one of these things, the main thing I'm trying to do is figure out how do I do pruning? How do I avoid looking at things more than once? Okay? How can I avoid doing that? Look at things I don't have to. Yes?
Use a hash table to make a state and check it.
Okay, so there's two different things. There's one solution is to note that many of my solution vectors will lead to the same board state. Does everybody agree with that? And there is not any reason to explore a board state more often under certain conditions. So your idea is going to be to do what? To maintain a hash table of the board states. And what's going to be in your hash table? Is it just that whether or not that state has been seen before?
You have big before and check it and check whether your step is bigger or smaller than your previous step.
So you're going to tell me the state and the cost it took to get to it, the number of steps, right? And so what is your search procedure now going to be? If you go and look something up, you generate a new step. You say, here's my new state in the board. Is this new state in the board is this current state of my board? Maybe at the beginning of construct candidates. Is the current state of my board something that I have already gotten to at least as fast? If so, there is no reason to continue searching from here. Does that make sense? So I claim that's one way to avoid a great deal of redundancy. It's not just whether the state is in there, but have I gotten to it? If I've gotten to it faster before, this solution right now cannot be extended to be a winner. But on the other hand, if before I found a path to this state that took 9 steps, and now I can get there in 7, it's still possible this will lead to a shorter solution. Any questions about that? So that's one improvement. What other improvements can we add to this thing to prune more quickly? Does everybody see that by pruning, what I mean is deciding that there are, in fact, no steps that will take me, no possible moves from this stage that will take me to a better solution than I already might know about. So if the number of steps to get to this point is greater than the best one I'd already seen, then there is no reason to continue exploring. And I have no moves from the candidate moves from this spot. Right? That's how I would implement it. How do you all understand that? Any confusion at all? Like, I don't understand what you're saying. What other pruning ideas can we use to make this faster?
Assign the ball as a global variable.
Okay, so one idea is a question of better bookkeeping. What you're trying to say here is, in my level of abstraction, I'm permitting you to reconstruct the board position from scratch every time. That might be excessively slow. Does everybody agree with that? And if I maintain a current board position as a global variable, then maybe I don't have to go and do the reconstruction. Okay? And that's probably a little faster. I've got to make sure I take back any move when it's appropriate, right? When I recur back, I'm going to have to take back my positions. But I agree, if you do the bookkeeping right, it will be a little bit faster. But only faster by a constant factor. Do you agree with that? It's going to take me a certain amount of time to build this thing, but this thing is constant. It's never going to be more than 50 moves. So as I thought, I'm not saying it's a bad idea, but does everybody see that that's not an idea of pruning? That's an idea of bookkeeping, data structures, right? Okay, and that doesn't mean it's a bad idea at all. It's a good idea, I think. It's undoubtedly a good idea, okay? But it's not as important as finding better pruning mechanisms. How else can we avoid looking at all these configurations? Okay? I still see several improvements possible to our search over what we've been talking about. Okay?
To calculate how many steps you still need at least to reach the final state.
Okay, so the first idea that seems important is, as we originally described it, we said find the solution to the end, then see if it's short enough. That's certainly wasteful because there's no reason to be looking for a solution of length 55. So we certainly should not allow us to generate any solution longer than 50. Or maybe we can cut it off earlier. If we have a bound, let's say that we know that our solution right now is of length 37. And it will take at least, what are we going to say? 21 moves to finish the job. There is no reason we need continue. Does everybody see that? If we can come up with a bound on how many moves remain, then we have a way of pruning earlier. Does everybody see that? How can we come up with a bound on how many moves remain? Let's think about that. There's probably a couple of different ways of doing it. Some of which are stronger bounds than others. Does anyone want to make a proposal? Yes.
Use Manhattan distance.
What?
Manhattan distance. This is to calculate the remaining step.
Manhattan distance, okay? So what is the Manhattan? Again, I come from Manhattan, okay? I know about Manhattan distance, okay? What is Manhattan distance? Okay? Manhattan distance says that it would just, I guess the idea that you want to use here is that this tile is eventually going to have to end up here, right? To get there, this tile is going to have to use at least 1, 2, 3 steps. Does everybody agree with that? And the interesting thing is that only once tile gets closer to where it's getting to. Does everybody see that on each step? So I claim it's now obvious that the sum of the Manhattan distances between where it is now and where we're trying to get is a lower bound on the number of moves remaining. Does everybody see that? Okay? And the cool thing about that is that that gives you a pretty good lower bound, or at least a pretty substantial lower bound. What is the lower bound on this case? I mean, this is, the lower bound here is probably already going to be, I'm just guessing, but from looking at this, it's probably at least 10 or 20 steps away, right? So you will be able to prune this at least 10 or 20 steps from the bound cutoff of 50, actually, right? Actually, how big a solution should you look for? That's a good question. At what point, what is the size cutoff solution that you should look for in this problem? Okay. How much? Read what it says. It says that you are limited to using 45, that each solvable puzzle can be solved at 45, but you're allowed to use 50. Which should you use as the size cutoff here? What? Who here says 45? Who here says 50? Who here said 45? You said 45, right? Why do you say 45?
My program, you run in 50, very slow, but 45.
So let's think what the advantages or disadvantages of this thing are. He's promising us, he meaning the guy who wrote the problem, is promising us that there is a solution within 45, right? So one possibility is that we look to 45. We know that there will, if we search, there will eventually be a 45 solution of size 45. Does everybody see that? And so we know we will terminate. The smaller we limit our solution to, the quicker we get cutoffs. So that's the good reason to go to 45. Does everybody agree with that? But what would be the good reason to go to 50? Okay? Does anyone want to defend 50? Why would you defend 50? Yes?
Because sometimes if you search to 50, it's faster to find a solution.
So there's a trade-off here. If we allow solutions of size 50, what if we live in a world where there is one solution of size 45, but a gazillion solutions of size 50? Everybody see that? It might actually be quicker to stumble on the one of size 50 than to find the optimal one of 45. Okay? So there's a decision here. Does everybody see that the question of which is right depends upon whether there's a lot of solutions or not very many solutions? Okay? So how would you decide which one is better?
Try both.
Try both and experiment, right? My guess would be to try the 45 at first. That would be my probably taste. But I can see why 50 might very well be a better thing. Okay? Any questions about that? How many people see that? So now you've got a lower bound. You've got a hash table. Is there anything else we can do to speed this thing up?
Never go back.
What?
Never go back, because if you move up, your next step will never move down.
Wait, what do you mean by never go back?
I mean, if the previous step is move up, then the next step will not be moved down. So
That's actually an interesting one. So you're saying that if you go up here, you don't want the next step to be down. Does everybody see that? Now that ideally could be, that's probably easier to recognize now. That hopefully would fall out of if you use the hash table properly. Does everybody see that? So that's an interesting question here. Does everybody see that? Any other ideas how we might make this faster? Okay? Degrees of control or not control that we have here.
Judge whether the star state, the first state is solvable or not in mathematical way.
Okay, so one thing that you're saying is that maybe because of your knowledge of this puzzle, or because you're very smart, you may know, in fact, that not all configurations, there are how many different permutations of this tiles? There are 16 factorial possible inputs. Does everybody know that? Agree with that? How many of them are solvable? Does anybody know that? Half. Why do you know half? Trivia that you picked up somewhere along the line?
I was reading about 15 puzzles.
Okay. So it turns out that half of them are, you say half of them are solvable. I think with Rubik's Cube I have the magic number that 1/12 of them are solvable. Okay? So it's not clear to me whether or not everything is. But you're right. In this case, if you could figure out why half the puzzles are not solvable, then use that to instantly answer the question, no. That would be good. Does anybody know why half the puzzles are not solvable? Okay. Supposedly this is what one thing you do, if let's say you have a younger brother or sister with this puzzle and you want to annoy them. The secret is you take these things, you dismantle the tiles and rearrange them so that into an unsolvable thing. And then you give them the puzzle back. Okay, they get very frustrated that way. Okay? But anyway, so what I would say is if you could figure out what is an unsolvable solution that would help. I don't offhand know how to do that. Do you know how to do that?
Actually, I just searching in the internet.
Okay, so you're searching the internet. That'd be one way possibly. But okay, that's what might be one idea, but I don't know how to implement it. Any other ideas as to how we might do faster? Okay? The only other idea that I would think about is, does it pay to order the moves? Up, down, left, right. In some particular order. Okay? To speed up what the search is. Okay? Do we have any idea here? Could we quickly decide which of these 4 move directions is the most promising? If we ordered the move directions by promising this, I claim you're more likely to get a solution faster than if not. How would we decide which one of these is most promising? Yeah?
Predict the result which is has lesser distance to the goal.
Right, so one possibility is to note that when you move a dial, is it getting closer to where it's supposed to go or further where it's supposed to go? That might be a heuristic to try to do it. Okay? Any other way to do it? Another way might even be to look ahead, use your hash table again, to decide whether that's going to be a more promising or less promising solution. Okay? Although that may be less clear. I would say you might want to, I see no reason why you shouldn't order it in a greedy type way. Okay? Any questions? Okay? Does anybody see any other ideas as to how you might order it? Okay? You could look ahead one move. Okay? And decide if that's going to help you or not. By basically going to the hash table as some kind of partial reference. Any questions? So between all these tricks, I would say you could help solve your problem. Okay? And doing the best solution is a, is going to be some kind of an art depending upon what you ended up encountering. Any questions? Okay. Any other ideas how you would make this go faster? Anybody who got this one working? How many lines of code was it? You get this working?
I did.
Who got this working? You did. How long is it?
100.
100 to 200. Okay? Any other questions or anything interesting here? Okay? So I think with that one, this one is now, I think, beaten down and we basically understand it. Any other questions? Okay. Which problem should we talk about next? Does anybody want Little Bishops, Garden of Eden, or Color Hash? Who wants to talk about which one do people want next? Bishops. Okay? Let's look at the bishops problem. Somebody who's done bishops, or someone who's tried bishops, tell me about what bishops is. You, tell me about what bishops is.
It's just similar to the equation problem. It's just to use bishops instead of queens.
Okay, so it's sort of like the 8 queens problem, except that instead of queens, you're using bishops. Okay? And any other differences?
It is not an NPC problem.
What?
It is not an NPC problem.
It is not a what?
NPC problem. The polynomial times solvable.
Well, okay, but it's not. Okay, so first of all, you're telling me this one happens to have a polynomial time solution. Okay? And you're right, but let's think a little bit more about it as backtracking first. Okay? Is this problem as a backtracking problem easier or harder than the 8 queens problem?
Harder because
Harder. Why is it harder?
because the k is not equals to 2 in the end. So you cannot know, like the 8 queen problem, you know that each row can only put 1 queen.
Okay, so let's think a little bit about this here. It's telling us that the board is 8 by 8, but there's a second parameter. They're not trying to put down the maximum number of bishops here. They're trying to put down k bishops. And k can be any number from 0 to n squared. For what values of k is it easiest for backtracking?
1.
What? Very small numbers, you're saying. Right? 0 is good. There's no one solution, right? In general, small numbers of solutions or large numbers of solutions or large k. Why? Because you're going to get a great deal of backtracking and pruning if almost everything is supposed to have a bishop on it. Right? You get a lot of pruning. The cases where this problem is very hard is when k is sort of in the middle someplace. Right? Because there's very little constraints for pruning, but still a lot of possible solutions. In general, there are something like 864 choose k possible configurations. So the most configurations would be when k was equal to 32. But when you get high enough, there's probably going to be a great deal of pruning, and then you can backtrack. But the trouble is that there's a mid-range here that makes this much harder than the 8 queens problem. Because there's room for a lot of things with very little pruning. Okay? Any questions about that? So who here tried to do this by backtracking? Okay, what happened to you?
Exist the time limits.
Time limits. What happened to you?
I do it in a little bit smarter way, but also get time limit.
I can get very fast if the n is equal to 8k is equal to 10, but for 11, 12, 13, 14 it's extremely slow. I do not.
Wait, for n equal to this?
N
Or
equal
for k? Or k? N is equal up to 8.
8, yeah, and when k is equal to 10 is fast. When k is larger than from 10 to 14 is.
Okay, so we're suffering for large k. Does everybody see? That's what I see what you're saying. Backtracking is suffering for large k for predictable reasons. Okay?
and then you can generate all the answers.
No, you can. I tried, but it's not. It always give me a wrong answer.
The other way to think about it is that you've got trouble. If you look at it, is here. For this value, this innocent looking 8 by 8, put 6 of them down.
This is fast. This one is fast.
To do it by brute force counting?
You use backtracking. This one is fast.
So this is where you're actually counting each one of these solutions, right?
Yeah.
You're able to count up to those 6 million solutions one by one. Fast still. Okay? But it's still nowhere near the target, right?
I think the largest should be 8 bits.
Largest
8 digits.
should be 8 bits.
8 digits.
8 digits, okay? How do we do this one faster? Okay? Is there anything else we can do to observe this one? To count the number of bishops, of solutions?
We can cut half of the solutions because the board is how to say this? The board is symmetric.
Okay, the board is symmetric. So one possibility that you might want to try to take advantage of is you're saying symmetry. That if you somehow, you might be able to
Cut half of
cut off half the search by dealing with symmetry. How would you deal with symmetry? Let's think about this. Okay? If we were doing this as a backtracking problem, pure backtracking problem, how would you deal with symmetry? Using the same kind of paradigm that we talked about. To avoid looking at 2 different solutions. Okay, what's your state space here going to be, by the way?
keep a map and a position. Just a map.
Wait, what's the, again, if I were doing this with our backtracking, what's our solution vector going to be for this problem?
Keep a map and the position, both of them.
Well, I want the solution vector. Again, we agree that whether we keep the state as a global variable or reconstruct it is a constant factor issue. Okay? For conceptual purposes, what is my solution vector here going to be?
Position.
The positions of the bishops, right?
Yeah.
So what would I do? I would have k slots. Okay? And I am going to, each number is going to be what? A number from 1 to n squared. Is that right?
Yeah.
Now, how would I take advantage of symmetry here?
I put the first in the up diagonal bricks, or the diagonal bricks, and the bottom diagonal will just ignore because it's equal to the up half diagonal.
Wait, so what you're saying now is if I have my board here, how do you take advantage of searching only half the search space?
I divide them by the diagonal.
By the diagonal, meaning what?
And the up one will be the same as the lower one.
Right, okay, so you're going to reflect the solution around the diagonal, right?
Yeah. Only for the first one. Only for the first one.
Only for the first one.
Yeah.
So the first queen, the first bishop you're going to put down, you're going to insist on what? How do you avoid doing the double counting?
That counting is another problem, and I use for the choose. Can I write it?
You may come up here, right? Yes.
For the double counting, it's kind of hard because, like, I have the map. We already know that because the bishops is in diagonal as their attackers. So we can only have this is 1, 2, 3, 4, 5. 7. So it's only 2n minus 1 at most.
Okay.
So any diagonal will be a subset of this. So I generate the like 2n minus 1 sets. I generate all those sets.
Okay.
And for each set I put in a multiplication.
Okay, so one thing that you might be saying here is, first thing to note is, this may not be, you're using a different state representation than I was doing. I had a number of k squares, each of which would go from 1 to n squared. You're instead proposing a solution vector of 2n minus 1 boxes, each of which could go from basically 0, meaning no bishop, up to n. Is that right? Or something like 2n. No.
And most n. And most n.
At most n. Does everybody see that? And what's interesting is he knows he can only put in 1 per bishop. Which one of these is better? I think I like this one better than I like this one, right? Because there's more structure in the solution. Okay? Any questions here? Okay? So how can we solve this problem more efficiently? Let's think about it. One thing is to note that it's a counting problem, right? So how do you count a counting problem? When we did combinatorics, how do you do counting? What is the first thing to do to try to solve a counting problem? Okay? What is it? I say write a recurrence. Is there a recurrence or a way we can count this thing? Any ideas? Okay.
I just try out all the possibilities.
What? You're trying what?
I just try out all the possibilities. So just
All possibilities. Let's see if we can write a recurrence for this. Because it's counting something. How do we do a recurrence? Okay? Again, if I were to do it, I would be saying, by my methods, C sub nk is equal to the number of k bishop solutions on an n by n board. Does everybody see that? Is there any way I can break this thing down? Break my problem of solving the n bishops problem into 2 smaller problems? Is there a way to make it independent problem, break it down in terms of independent problems?
break down by the diagonal into choose problem.
What?
Just like I said, I choose k from the 2n minus 1 diagonals.
Right?
So break into several small problems.
Okay? I'm not seeing that. Can I break this thing into, can I break my n bishops problem into 2 problems that I can consider independently? Let's think about that. What are the 2 problems I can solve this thing in to consider it independently?
The black will never attack the white.
Does everybody see that in bishops you get a black bishop and a white bishop, right? A black bishop cannot attack a white bishop. Does everybody agree with that? So what if, is there a way I can break this thing down into white problems and black problems and solve them independently? Is that reasonable? How could I do that? Let's think about this. One possibility would be if we think about a backtracking-like thing. You take a look at just the whiteboard that remains, right? What is the whiteboard after we delete it? It's going to sort of have these squares together. Does everybody see it? The whiteboard is going to be these things. One possibility is that I find all white solutions with a certain number of bishops, right? And all black solutions with a certain number of bishops. How could I combine that? The product? Okay. How can I formalize this thing?
Like the B indicates the B and K indicates the number.
I think it's going to be something like this. the sum as I equals from 0 to k
Black.
of C sub black sub n comma I
C white.
what?
C white.
Does everybody see that this would work? Right? If we break it into separate problems. Now, if we only consider searching, counting on white and counting on black, okay? Now we can combine it, okay? And this has certain nice properties to it, right? One property is that each one of these should be, in some sense, half as many possibilities, or less, right? There's somehow half as many squares. It seems to me this problem is a lot easier to solve. Okay? Does everybody agree? If we could solve C black and C white, okay? For each value I goes from 0 to k, we would have this answer. Does everybody agree with that? How would we modify our program? How much different, though, is the white case from the black case? Can we use the same program for that?
No.
No. You're telling me no. Okay, why not?
You can see that the black is 1331 and the white is 242. So
Well, wait a second.
you
You're
can-
saying that this one here, there is a 1.
I mean, the structure of these two boards is different.
Are the structures of the white and black boards different?
Yeah, you can multiply by 45 degrees.
You're saying they're multiplying by 45 degrees and they're not different, are they? So here's a question for you. Is CW sub n comma k equal to C black sub n comma k? You're saying no. Why or why not? What?
If n is even, that's true.
If n is even, that's got to be true. Why?
Why?
If n is even, let's look at this thing. Here we've got n equal to 4. I have to believe that the whites and the blacks, that the answer is the same for this board.
No.
Well, let's think about that. Why not?
Oh, yeah. Because
Does everybody see that somehow there is some symmetry here? What is the symmetry to make it the same? Okay? You say transform, how much do I have to tilt it?
90 degrees, and you can see that the black.
If I turn my head 90 degrees, okay, I'm believing you now. I'm just trying to do that in my head. I have a hard time shifting by 90 degrees. But it's pretty clear that these two are symmetrical cases. There are 2 spots per row. They interleave with each other. It is clear that by symmetry, these two are going to be the same if what? If n mod 2 is equal to 0. Is that right? Does everybody agree with that? And now, how do we handle it, though? That's great because that will simplify this for certain cases, right? How do we deal with it when they're different? When it's not 0? Okay? Let's now try a 3 by, what do you want, 3 by 3? Here we've got, in this case, this, versus this one. Okay? How do we deal with the case where it's odd? Is there a way to simplify it further? I don't yet see it, okay? But in my art of arts, I kind of believe. So we've got this recurrence. We've got now three parameters, C, CB, CY. For even ones, these things are the same, okay? For odd ones, still we've probably got to count it out differently, okay? Unless we can see a little bit more insight. But this, I claim, these ideas now take us to the point where you can use some combination of a recurrence and backtracking to solve this. Is that how you did it?
Yes.
Okay? Still not fast enough. So maybe we don't want to do any backtracking. Maybe we want to keep working on this and see if we can get a closed form now for this particular answer here. What? Well, once you have a recurrence, you can use it to solve it. What though I don't see.
No, I mean that you can use DP to solve the CB and CW. You do not need to.
Don't use that because
Okay, what you're saying now is we've got a recurrence still on, we've got a total of 3 recurrences. Okay? What are the basis cases that we would want to use? Okay? The basis case would seem to be, you could presumably count out what C white and C small are for very small values. Okay? Do we have enough information now to complete doing this by dynamic programming? What are the basis cases? Okay?
Dynamic programming for solve the CB and the CW.
We need recurrences for CB and CW. We need recurrences for CB, B and CW, right?
Yeah.
So what is that going to be now? CW sub n.
Well, the structure is different. We need a different structure to solve this problem.
Okay?
you need to transform the chess into another form.
Okay.
This structure is called solved by DP, which is inverse inverse.
Right.
So I can shift it so it can be like this.
Okay.
We have some values. And now each bishop is only this. So I can use this like this structure. And each row I can only put one bishop.
We agreed to only put one bishop here.
For each row. Yeah, so so I can swap those rows to put it like this way. Those two equally the same the same solution.
Okay, I'll admit I'm not seeing what you're doing here. Okay?
In this way, each row and each column, you at most can put one digit.
In each row and each column. So, each row you can only have one vision. So this is the same. So this two have the same solution, number of solutions.
Okay. So, can you write out your recurrence?
For like columns, is the number of columns. It is the number of columns on each row. And this is the row and I indicate here is the number of
Okay.
I think.
Okay. Some way or another, I claim you've got to write a recurrence for this. I still believe that I can come up with a recurrence for C white and C black. Okay? As a function of n. Okay? And that's how I would be trying to do it. You have an idea of an alternate representation for this. And I believe that and there's probably a way of making that work. I don't really doubt that. On the other hand, I would probably be sitting down here now and trying to think a little harder about, I know what the recurrence here is. For, this is basically, I know a couple of things. This is basically for the case of 2n. What I now need to know is what is CW of 2n minus 1, 2n minus 1 or plus 1, k, and CW black of 2n plus 1k. Okay? I know how to simplify it in the case where they're even. Okay? I still think that I want to figure out if I were doing it, and we're not going to have enough time so I can speak in a vacuum now, but I would still think that there is a recurrence for this kind of a thing. How many white solutions are there on a board of this, or how many black solutions are there on a board of that? Okay? And if I have that, then I have my dynamic program. You have an alternate way of seeing it. If it generates a dynamic program, you're done. Okay? Even if not, if it takes it small enough to the point where you can then use your backtracking, that might be another way of doing it. Although you tell us this hybrid solution doesn't work. Okay? So think about it, see if you can come up with a recurrence for that. That, I guess, is the answer on this one. Any questions? Okay? So this one looks a little challenging. But let's look at the other problems now. Which other problem did people look at? How many people looked at the Garden of Eden problem? Okay, how many people have looked at it? How many people solved the Garden of Eden problem? Okay, someone tell me what the Garden of Eden problem is.
You will get solve a formula and you check it. Is the final state? Is there any previous state to F root to the final state? The answer is can you find a previous state from this one?
Right. So the question here is, we have a state of our cellular automata here. We want to know, is there a previous state? Does everybody agree with that? Right? And such that it generates this by these rules. Does everybody agree that basically you're given, if we look at the problem, some kind of a cellular automata rule, which once you parse it is readily understandable. Once you exploded that rule, one of the 256 rules gives you basically the bit pattern of, for every window of 3 spots here, what can generate a 1. Does everybody see that? So what would the solution to this thing be? Okay? We do this as a backtracking problem, right? What is our solution vector going to be? Let's think back to my formulation of backtracking. What is the solution vector going to be? What? We say backtracking doesn't work. Why doesn't it work? Let's try it first of all. What is the backtracking? What is the solution vector? An n-element vector where a sub I is going to be equal to the contents of the ith bit, which you're telling me can be 0 or 1. Is that right? Now, what is my construct candidates vector construct candidates going to do? I have a partial solution of 0s and 1s. What are the candidates for this spot? Is it 0 or 1? Under what condition is it not 0 or 1? So one possibility is I allow 0 for 1. I always allow you to make a 0 or 1, right? And then at the end I test if my string generates this. Does everybody agree with that? Now the trouble is that's going to take 2 to the 32 time, right? Is there a way I can do backtracking to prune it so I don't construct all possible solutions? Right? So what should I put down here? What are my choices for this spot? Is it a 0 or a 1? Under what condition is it not a 0 or a 1? You know, what conditions is it not a 0? Is a 0 not a candidate here? What?
One of the first two is 0, 1.
Well, I claim that if I have the previous 2 positions, putting down a 0 is going to decide what the value of this is going to be. Does everybody agree with that? So this rule is either going to be true or false. My choice of a 0 or a 1 here. I can only have a 0 if the rule here generates the proper thing. Does everybody see what I'm doing here? So my immediate sense as to how to do it is I'm going to prune it by allowing a 0 or a 1, by disallowing what causes a problem. And maybe it'll be a 0 or a 1, or maybe it will only be one possibility, in which case I can grow without worrying about it. Or maybe it is 0 possibilities, in which case I can backtrack. That's how I would do this one. Has anybody tried it this way? What happened?
It's okay. Do the direction. Firstly, we assume 4 possibility is 0, 0, because we need to have an initial state for the first one and the second one to predict the third one.
Okay.
So we have 4 states, 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1 first.
Right?
And then we can do the backtracking and punching and to predict the third one and the fourth one, and then etc.
Okay. So you're saying that, I mean, you're saying you explicitly start with the four first two possibilities. That's one way to do it. The other, and maybe even a better way to do that. The other possibility is your move generation is smart enough to know that in spot 0 or 1, you can try both possibilities. Right? Any other ideas here to speed up that search? Okay, is there any possibility we have to speed up search that might be helpful?
I think it's enough already because I can solve it by using this method.
Okay, so you're saying you can do it, so therefore this is enough. This is an educational thing. Is there any way we can speed this up further? Let's think about it. Okay? What other freedoms do you have here? One thing to note is that, that you don't necessarily have to start at the first spot of their solution, right? If we decided that part of the string was more constrained, we could conceivably do a circular shift on the input, a certain number of positions, to start working on the harder part first. Okay? Do people see what I mean? If you're doing the backtracking search, you want to work on the harder part before you work on the easy part. Because you don't want to go laboriously build up something that's then going to break at the hard part. So there's probably some analysis you could do to figure out where is the most constrained part of it. And what I think the issue here is, you know, if there are, if it's hard, if very few rules, here's one way to think about it. The more rules that make zeros, the easier it is to make a 0 than a 1, right? So maybe using the rule count might tell me where is it easier or hard to do it. That'd be one way I might improve it. Okay? Any other ideas? Another question is I could grow it in principle. I don't have to necessarily grow it all in one direction. If for some reason I thought it was going to be harder, you know, I would want to grow it in the direction where it is harder first, right? So if there were two choices here, and there was one choice here, I would probably rather put down the one choice here and move on rather than go where there's two choices. Do people see what I mean by this here? If there's a fixed decision, because there's 0 or 1 possibilities on one side, I might be better off looking at both sides to decide where is my next move going to be. Any questions about that? You say it's not necessary, but we have that freedom if we want it. Any questions? Any questions about cellular automata or anything else about this work? Cellular automata are interesting things, but we won't have time to talk about them. Any questions? Final one is the color hash problem. How many people tried to do the color hash problem? How many people did do it? Okay. Who wants to tell me what color hash is? Somebody else. What's it? You today, Aaron. It's hard for you today.
There are two wheels, and each wheel consists 12 pieces, and there are 3 pieces in common. You can load
3 common pieces, right?
You can locate any one, left one or right one in clockwise or counterwise.
Right, so we can rotate this thing. It looks like there's only, to be stable here, I've got to rotate one of these footballs over, right? And so there's only 4 football stages. This one, 2, 3. How many football stages are possible here? Okay, I could rotate it over 2. This football would be there. I could rotate it over 4, this football. 5. So I could rotate 0. That's 1. That's 2. That's 3. That's 4. There's 5 possibilities. Does everybody see that?
But each step you can only advance 2 pieces.
Right.
You can't advance 4 or 6 or 8.
Oh, I see. You're saying that for a step to be counted, they're only going to allow me to go 2 forward or 2 back. Is that right? Okay, fine. And now the question is to find a solution. You need to find the minimal solution. Okay? So how do we do this one? This puzzle looks very complicated compared to the others. I think that's my immediate reaction when I look at this. But what's our solution state going to be? What is our solution vector in our model here? What would you put the vector as being?
Each element is 4 different operations.
From each state, there's 4 possibilities, right? Left wheel up, left wheel down. Is that what it is?
Yes.
Right wheel up, right wheel down. So there's only 4 possibilities, right? We could represent the state space as being this. Does everybody see that? How long is the longest possible solution here? What? 16? I think that's what they said, right? They said if you can't solve it in 16, give up. Is that what they said? So this is 16. Okay? And now is this basically dealt with the exact same way we dealt with the 15 puzzle? Is there anything more complicated here? The representation of the board seems more complicated, right? But as far as the search procedure goes, I don't think this is any different. Is there anything more subtle here? We may need a new lower bound, right, to do this efficiently. What is a lower bound on the number of moves? Okay? Can we look at a board configuration and tell me something about what a lower bound on the number of moves is? Okay? To make it analogous to our 16 puzzle, 15 puzzle problem. Here is the right solution, right? Here is our input. How would we compute a lower bound on how many moves we need? Okay? One way we could do it is say if it's not the solution, we know we need at least 1. That's a lower bound. But that's not a very good one. Can we find a better lower bound? What would be a lower bound that we might propose? Okay? Any ideas? I would think that the lower bound would be something like you've got 3 tiles. Well, let's just think about it. When we do a rotation, okay, each tile on this side moves how many spots? It moves 2 spots. Does everybody agree with that? So one question is to try to think about, again, what the distance is. How much movement is created? And when we do one of these distant moves, how much closer are the pieces afterwards than before? Okay? It's a little bit more subtle. We have to try to think this thing out a little more carefully. But I claim that there is, again, a lower bound that we can figure out. Anybody who did you do this problem?
Yeah.
Did you have a lower bound?
Yeah, I just use A star algorithm to solve it. And easy to solve it.
Okay, now there's another way to do it, other than backtracking. We was using the magic word A star. What is A star algorithm? How many people here know what the A star algorithm is? How many people don't know what the A star is? Okay. Depth first search. Backtracking, we said, was like depth first search. Depth first search is a good thing, but it sometimes goes very deep away from a short solution. Okay? Breadth first search is a good thing, right? It goes like this. What's the problem with breadth first search? That way we did a search in a breadth first manner. We would guarantee that the first time we find something, there would be a shortest possible thing. But what's the problem? The real problem usually is actually memory. You've got to keep track of whole state of all possible things across this tree. Whereas in depth first search, it's only according to the depth that you have to keep track. A star is a best first search, essentially. Right? It takes this move that looks like it's in the best possible direction. That's what a star does. Okay? But to be correct, once it finds something, okay, it's got to somehow search all other possibilities that haven't been proven worse than it yet. That's really what a star is doing, right? Yeah.
A star is just a combination of best first and
best first and once you've found something. It's best first where you're taking into account both the cost so far and the lower bound. And you're stopping when the lower bound on anything that hasn't yet been explored is not is worse than the best solution you see so far, right?
If you have an admissible heuristic, it's the first solution is the best solution.
Okay? So it's a question of if you have the right properties of your upper bound and your lower bound, and how you search it, good things can happen. That's really what A star is doing. Okay? So you could do this by A star. You could have done anything else by A star, but recognize what the difference is. Backtracking is, I think, particularly simple because it's a depth first search. Okay? I don't know if there is a particular advantage to A star over backtracking in this case. Okay, you did it with A star because you know about it. What is the advantage there?
A star you can, because it uses a priority queue to estimate the step, so you can find your final solution earlier than the backtracking. Because backtracking, you need to generate the case to.
So the question of which one is better depends something upon the properties of your search space. Right? It is not always clear that A star is going to give you a better solution quicker. Okay? Just like it's a question of whether there are a lot of solutions, whether you need a solution that's short, how good is your pruning thing. So A star is a respectable thing. But I would probably have done this by backtracking. It would have been my immediate sense, just because I personally feel more comfortable with it. Did anybody try this by backtracking? Does anybody have a reason why it's not going to work by backtracking? Okay? So if you don't know about A star, I recommend trying backtracking. Let's see what happens. Okay? Any questions here? Okay, thanks for your attention. We'll talk to you guys next class. Okay? But let's see how we do on it.